Hello guys, in this lecture we are going to look at the addition reaction. Now what is the addition reaction all about? Before now, we know we have three classical organic reactions, and then we have a fourth kind of organic reaction that is not among the classical organic reactions. Now the three classical organic reactions are, we have the substitution reaction, and then we have the addition reaction, we have elimination reaction. Now, the fourth kind of reaction, which is not regarded as a classical reaction, is the rearrangement reaction. This reaction, okay? So we said we have three classical reactions. We call this the classical reaction. And our topic of interest today will be the addition reaction. So what is the addition reaction all about? Now, the addition reaction is mostly exhibited by compounds that have by compounds that have unsaturated bonds, okay? Compounds that have unsaturated bonds, okay? Now, in organic chemistry, the major unsaturated bonds we have the double bond, and then we have the triple bond, which can be seen in the functional groups such as the alkene, the alkyne, the alkanoic acid, then we have alkanol, which are the ketones, and then we have the alkanal, which are the aldehyde. Okay, so these are the major functional groups that have these unsaturated bonds. Are you getting it? We have the nitride also. For instance, see, this is the nitride. Are you getting it? We have other functional groups which we are not disposed to name now because we are not going to talk about them. So our major focus is on the alkenes and the alkynes in this lecture. What we are going to focus on is the alkenes and the alkynes. Now, what are the alkenes? The alkenes are a class of compounds that have a C double bond carbon. So any class of compound that have this C double bond carbon bonds is an alkene. Now the point of unsaturation is this point here. That is this double bond here, okay? And then we have the alkynes. The alkynes are C triple bond C, something like this, okay? These are the alkynes. And then we have the alkanones. The alkanones are having C double bond O, and then the alkanal, this arrow alky, and then the alkanal is arrow C double bond O and then H. But our major focus will be on the alkene. Now the addition reactions can be in two forms, or it can be initiated by an electrophile. Now, if it is initiated by an electrophile, you call it electrophilic addition reaction. Electrophilic addition reaction. I'm going to use this to indicate reaction, okay? So whenever you see this, know that I'm talking about reactions. And then we have the nucleophilic addition reaction. If the reaction is initiated by an electrophile, you call it an electrophilic addition reaction. However, if it is initiated by a nucleophile, you call it a nucleophilic addition reaction. Now, another thing that we also need to take note of is why or how does this reaction actually occur. This one we are going to be talking about now is mostly on the electrophilic addition reaction. Okay, electrophilic addition reaction. Now, the electrophilic addition reaction, how does it occur and why? Now, it occurs, or less electrophilic, it occurs between the double bond of the alkene and then an electrophile. So we have this C double bond C, this and this. This is the double bond of an alkene, and then we have an electrophile. Okay. Now, this double bond of an alkene is the pi bonds here. You know, in every double bond, one of the bond is a pi bond, and the other one is a sigma bond. Now, the pi bonds of alkenes are weakly held. Are you getting it? They are weakly held. Hence, you can call them electron donate. They can easily donate the electron of the pi bond of alkene. Are we getting it there? Hence, you can call them that they are perfect nucleophile. So the pi bonds are nucleophile. And you know what a nucleophile does, according to what we've explained in other of our videos. But if you don't know what a nucleophile do or does, know that a nucleophile, it attacks an electrophile. It's an electron donating group. Okay? So the first step of the reaction or the first step of an addition reaction is this. Now, before we even talk about the first step, you know, we are talking about an addition reaction where an electrophile attacks a double bond. Now, what are we expected to form at the end of the day? We are expected to form a saturated bond. So we can say that this reaction is usually between unsaturated group, in this place alkene, right, plus an electrophile to give a saturated group. Okay, to give a saturated group. So let's look at it together. How does this reaction occur? Now, the first thing is this positive charge here is a perfect electrophile. It's a strong electrophile. Let's take it that way. So we said the first step in electrophilic reaction is the attack of this double bond on the electrophile. When it attacks the electrophile, one of these carbon must have donated its electron to attach with the electrophile. So that one that donates its electron now become positively charged. Okay, so we are going to form something like this carbon. Are we getting it? Then we are going to have the carbon. Then we have this group here, and then here becomes positively charged, and then you have something like this, right? And then you have something like this, and then you have carbon. Sorry about that. And then you have hydrogen. Now this electrophile will be here, okay? And then you have this one, this one. This will be the product of the reaction whenever this double bond attack this, okay? This is called a carbocation. Okay? Now this carbocation now, it's a positively charged ion. Are you getting it? And it can easily attack a nucleophile. Do you know why? Because nucleophiles are what? They are electron rich and they attack a positive what? Charge. So this is the first step of the addition reaction, whereby the double bond electrophilically attacks the electrophile to form a carbocation. Okay? Then the next step is the carbocation react with a nucleophile to give the product. So what do we have here? We have the positive charge here. This carbon, positive, this, and then you have this, and then you have hydrogen. This is not hydrogen. This is electrophile. This is not hydrogen. I'm just trying to use. These are any bond. It can be anything. That is the implication of that. Okay, plus Nu, then negative. You know this nucleophile is electron rich, right? So what will happen? The nucleophile will attack this site of positive charge. Are you getting it? Now, if I want to make things easier, I can decide to draw it this way. Any one of the ways are correct. You have positive charge. Are you getting it? And then you have the hydrogen. Is that not so? And then you have the what? The hydrogen. Or these are not hydrogen. Before I start calling hydrogen over and over again, I can decide to write it this way too. And then I put the positive charge here, right? And then I put something like this. This is the electrophile. This is this. These are bonds. Plus a nucleophile. Now, what do you say is a nucleophile? We say nucleophile is a nucleus-loving species. It loves a positive charge. So we have the electron with this on top. Then what happened? This one attacks here. As it's attacking here, what will be the product of the reaction? The product will be carbon, and then you have what? Nu, which is the nucleophile that attack, the NU should be in purple, which the nucleophile that attack, okay? And then you have your bonds, okay? And then here is your electrophile, something like this. So this is the product of the reaction, which is a saturated compound. So in addition reaction, the first step is formation of carbocation by the electrophile. Then the second step is addition of the nucleophile to form the product. So let's see an example. Now you have an example here. Say predict the product of reaction between but2-ene and hydrogen bromine. Between but2-ene and hydrogen bromine. Let's see the product of the reaction between but2-ene and hydrogen bromine. What is the structure of but2-ene? It's something like this. You have CH3, right? Then, sorry about that. You have CH, double bond, CH, and then CH3. This is structure of but2-ene plus hydrogen bromine. Hydrogen bromine is what? Is HBr. Let me put it here. Now, this one, you can actually do this in just a few steps. Instead of, first of all, breaking this down to form electrophile, whatsoever, you can just say, okay, you know this double bond is what is attacking here, right? Then what happens to this bond? This bond will kick here as a negative charge, okay? And when it kicks in there as a negative charge, what are we going to form? You are going to form something like this, which is CH3 and then CH. Now, if this hydrogen attacks here, which is the one that is coming, it's going to form a linkage here. The hydrogen from the bromine. Are you getting it? And then if it forms a hydrogen there, then what are we going to form here? You're going to form CH, and then you're going to form a positive charge here, right? And then CH3. Now recall that as this one is packing in, what happens? This bromine will become what? An ion. So it will form something like this, Br with its electrons, right? Then you have the negative charge here, okay? So this bromine ion now is a perfect nucleophile, okay? Bromine ion is a perfect what? Nucleophile. So we have the bromine ion, which has this amount of electron. So this bromine ion now will do what? We attack here, right? Attack by red pen. So this bromine ion now will attack this positive charge here. So the product of this reaction will become CH3, CH. Now this hydrogen plus this hydrogen, you can decide to put it up here, right? To make it easier. And then CH. Here is what? Br. And finally CH3. Let me rewrite the product here. CH3. Then we'll have CH. Hydrogen is on top here. CH. Br is on top here. And then we'll have CH3. And this is the product of this reaction. What is the name of this product? We say this is 2-bromo what? 2-bromobutane. Okay? So it forms 2-bromobutane. So that is the product of that reaction. 2-bromobutane. Okay? That is the product of that reaction. So if I want to give you an assignment now and I change this to pent2ene, I say react this with hydrogen bromine. What do you think will be the product of the reaction? Now that will be your first assignment, okay? Work on this. Predict the product of the reaction between but2ene and hydrogen bromine. That is the one I'll solve. Now you predict between pent2ene and hydrogen bromine, okay? Now, the next, there are different types of addition reactions, okay? We have different types of addition reactions. The one we just did is a hydrohalogenation. This one we are going to talk about that is hydration. Now, to hydrate means what? Addition of water, right? Water. So let's add water to an alkene and see what it will give to us. Plus H2O. Now, when you add water plus H2O, it's going to give us C. Then the water, OH we add here, and then hydrogen we add here, and then we have the bonds, which are this, this, and this. Are you getting it now? So whenever you add water to alkene, it's going to give us alcohol. It's going to give us what? Alcohol. And the product follows what we call the Markovnikov rule. The product follows what we call the what? Markovnikov. Are we getting it now? Rule. Now we can still remember Markovnikov rule from PCH321, right? which states that while you are adding, the hydrogen should go to the carbon having the highest number of hydrogen, and then the OH goes to the carbon with the fewest number of hydrogen. Okay, so for instance, now let's say you have pent2N, the one, or let's say propene. Propene is CH3. Then we have CH double bond CH2. Let's say you add water, right? Markovnikov rule in the appropriate reaction condition. What do you think will be the product of this reaction? Now, according to Markovnikov rule, if you can still remember what we did in year 1, we said this one will split into H and OH. Not even in year 1, in year 2. And then what happened? The hydrogen goes to the carbon with the highest number of hydrogen, and then the OH goes to the carbon with the fewest number of hydrogen. So this is going to give us CH3 and then C. Now, when this OH attacks this carbon, it's going to give us what? OH, and then we have CH. Now, when this H attack here, you're going to give us CH3. And what will be the product of this reaction? This is 2-propanol, or we can say propan-2-ol. Now, you call it 2-propanol, or you can call it propan-2-ol. Okay? So that is the product of that reaction. It follows the Markovnikov rule. So if you are given any question, you should be able to know which of them we are actually working about or talking about. This is hydration reaction. Now, the next one is hydrogenation. Hydrogenation follows hydrogenation is addition of what? Hydrogen, okay, to alkene with the appropriate catalyst. Okay, so for instance, if this is an alkene, you know, we are just using this to represent an alkene, which is like a formula for alkene plus H2 in the presence of catalysts such as palladium or platinum plus heat. Now, if you add this plus this together, what is it going to give to us? The product of the reaction would be C is going to give us an alkane. Okay? So whenever alkenes are hydrogenated, it gives what? Alkanes. For instance, if you have, let's say benzene, the structure of benzene is something like this. Sorry about that. Structure of benzene, something like this. Okay? Benzene is something like this. When you add benzene, when you react it with hydrogen, okay? H2, in the presence of catalysts such as platinum or palladium plus heat, what do you think will be the product of the reaction? Now, listen and listen very well. Each of these molecule of hydrogen, now if I say H2, I'm talking about molecule. Each molecule of hydrogen can only break one bond. Are you getting it? Or can only break one pi bond. So we say 2 molecules of hydrogen will break how many pi bonds? To break 2 pi bonds. So 3 molecules of hydrogen will break how many pi bonds? To break 3 pi bonds. So we are going to put 3 molecules here. So what do you think will be the product of the reaction now? It will give us a cycloalkane. Okay? So this is cyclohexane. So you see that whenever the alkanes are hydrogenated, the product is usually what? Alkane. So if I hydrogenate propene, it means the product would be what? To give us propane. Okay? So you see how easy it is. So if I should give you, for instance, let's say I give you this compound CH, and then we'll have CH3, and then hydrogen, and then we'll have H and CH3. And I say hydrogenate this by passing it through platinum and hydrogen. Okay? What will be the product of this reaction? It's very easy, right? It's going to give us hydrogen, carbon, then we'll have what? CH3. This bond is going to break, of course. And then you are going to have one hydrogen attached here, right? So if I want to write it in a way that to be more presentable, here becomes CH3, hydrogen, hydrogen, carbon, CH3, hydrogen, and hydrogen. And then this will be the product of the reaction. So you see how alkanes can be hydrogenated. Now, the next one we are going to look at is dihydrosylation. Dihydrosylation. Now, talking about dihydrosylation, it means adding 2 OH group. That's the meaning of dihydrosylation, okay? So, for instance, if I have something like this, so dihydrosylation. Now, As name implied, di means two. Hydroxy means what? OH. So dihydroxylation means addition of two OH group to an alkene. Now, when you add two OH group to an alkene, what are you going to form? You are going to form two hydroxy group on top of an alkene. Now, it's an oxidation reaction. So we have something like this: C, double bond C, hydrogen, hydrogen. Are you getting it? And then you have the peroxide, right? Peroxide is something like this: H2O2, which can be written as this, okay? Then you have oxidation. If you oxidize this with peroxide, what is it going to give to us? It's going to give us something like this. You have the OH group on top, you have the hydrogen, you have the hydrogen, you have the carbon, you have the OH, you have this hydrogen and hydrogen. Now, this is the product of this reaction. This is a diol. Are you getting it? So whenever they are dihydroxylated, it forms a diol. Now, why did I call it a diol? This is an alcohol group, an or, another alcohol group, another or. So two or are joined together. What do you call it? You call it a diol. Okay. So this is a diol. Okay, and that is the product of that reaction. So, for instance, if I give you something like this and I ask you what will be the product of reaction between this and this plus, then I put peroxide here, which is, it can be in the form of H2O2. You may see it like this, right? Then you have oxidation. What will be the product of the reaction? Product will be a diol. So you have C double bond C. No, C double bond C will be out, right? Then what are you going to have? You have the OH here attack at the seat of the double bond, right? And then you have CH3. Then you have hydrogen. Then you have OH. And then you have CH3. And then you have H. And this will be the product of this reaction. So you call this 1, 2, 3. So you call it 2,3-butadiol. Okay? 2,3-butadiol. And that will be the product of the reaction. So that is for dihydroxylation. Now the next one we are going to look at is oxidative cleavage. Are you getting it? Now, oxidative cleavage is called ozonolysis. Ozonolysis. Now, what happens in ozonolysis? Look at it. If you are given an alkene like this is an alkene. Are you getting it? And then you react it with ozone, O3. Oxidation reaction. What do you think will happen? This double bond will split. You learn the mechanism in Waba's part. When this double bond split, it's going to form two carbonyl group. So when this one splits, it's going to form something like this: C double bond O. Okay, we're going to form double bond O plus something like this. So you see that this one split into two. You add oxygen here, add oxygen here, and this is a carbonyl group, carbonyl, and this is another carbonyl, and this is the product of this reaction. So it is also used to determine the point of unsaturation in an organic compound. Are you getting it? For instance, if we have something like this given to you, same thing. Let's say you have something like this given to you: CH3, hydrogen. Then you have CH3, and then you have CH3. Now recall that this can also be written as CH3 brackets. How many of them are here? 2. So you have 2, and then you have this carbon double bond C, and then you have H and CH3. Now you may be given in this form. Know that these two things are what? They are the same. So if you react this, pass it through ozone, is an oxidation reaction through O3. What do you think the product of the reaction will be? Now this double bond will split here, right? If it splits, it's going to form something like this: CH3, C, CH3, double bond oxygen, plus C double bond oxygen, plus CH3 and hydrogen. Now this is what? What functional group is this? This is a ketone. And what functional group is this? This is an aldehyde. Now you discover that the product of ozonolysis depends on the nature or the structure of the alkene that was given. Are we getting it now? If the alkene that was given is in such a way that it's going to yield to aldehyde, it's going to yield to aldehyde. For instance, let's say I remove this CH3 from here and I add hydrogen to here. Now, if you split this with ozonolysis, it's going to yield to what? Aldehyde, because this is going to give us something like C double bond O, CH3 and hydrogen. Is this not an aldehyde? It is. Then this is going to give us CH3. Then we have hydrogen, C double bond O. Is this not an hydrogen? This is an aldehyde too. Are we getting it? However, if we change this to CH3 and then CH3, what will be the product here? Here becomes CH3 and here becomes CH3. Are you getting it? This case now, it has yielded how many ketones? 2 ketones. So the product can either be an aldehyde or a ketone or a mixture of both aldehyde and ketone, as in this case that we have here. It's a mixture of both aldehyde and ketone. So that is what oxidative cleavage is, which is ozonolysis. Now the next one we are going to look at is epoxidation. When alkanes are oxidized, they form epoxide. Okay, something like this. Epoxide are cyclic structures. Are you getting it now? So if it undergoes oxidation with oxygen, it's going to form an epoxide. An epoxide is a cyclic oxygen structure, something like this. Okay, then we'll have bonds like this. Okay, this is what is called an epoxide. This is what? An alkene. So when you see that the reaction is epoxidation, this is what is going to give to us. Okay, so for instance, if you have a reaction like this, and then you have, let's say, this CH double bond CH CH3 oxidation, and then you have oxygen. What do you think will be the product of this reaction? Now this reaction is going to give us CH3. Okay, then we are going to have CH, right? Then we are going to have this oxygen here linked to this double bond. Now it's at this point that it's always added oxygen, and then this double bond will what? Will break. Okay, so what are we going to have? The structure is going to look like something like this, and here becomes CH CH3, and this becomes the product of this reaction. Or if you want to make it to be the way it is there, you can decide to say this is a carbon here, and here is what? CH3, here is what? Hydrogen, and then we can have this carbon here, carbon, hydrogen, hydrogen, and CH3. So that is the product of this reaction, and that is what epoxidation is all about. The next one we are going to look at is halogenation. Now, alkenes can react with halogens, right, to form alkyl halide, alkyl halides or dihalides, to form dihalides or vicinal dihalides. Now, let's look at something like this. These are halogens X, where X can be chlorine, bromine, or iodine. Okay, when they react, what do you think will be the product of the reaction? They're going to give us C, and then here is X, here becomes X, and then you have this bond like this. Are you getting it now? So that is what is obtainable. Now the same approach is what we have been doing since. For instance, if you have a reaction like this, still the same reaction, okay, and then you react it with S2, what do you think will be the product of the reaction? Let's say you react this with bromine. This, we attack this, and then it's going to form CH3, then you form C, H, and then you have B arrow, C, H, CH, and then you have Br, and this is the product of the reaction. Okay, this is the product of the reaction. So that is for halogenation. Now let's look at the next. Radioselectivity of addition reaction. Now when we talk about radioselectivity, we mean that whenever addition reaction occur, more than one product can be formed. Are you getting it? More than one product can be formed. But the question is, which of the product will be the major product and which will be the minor product? Now, before we talk about radioselectivity, we should look at the stability of the carbocation that is formed, because we said that addition reaction usually involves the formation of what? Carbocation. So let's look at the carbocation that will be formed. The carbocations that are formed, the stability of them. Now, from our knowledge before now, we say tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl cation. So the major product will be the one that a tertiary cation will be formed. Are you getting it? Or a tertiary alcohol will be formed. Or not alcohol in this case, a tertiary bromine will be formed. Okay? So let's look at these two reactions and then see the one that will give the major product. If this react with this, according to what we said, right? This bond can break. And when this bond breaks, one of these hydrogen attacks here. Here can become positively charged and here can also become positively charged. So we have two places that can become positively charged. It's either it's on this carbon here or this carbon. There are two carbons at the seat of the double bond. Any of them can become positively charged. It's either this carbon or this carbon, right? So what we are going to have is something like this. CH3, CH3, positive. Then we have CH and then CH3. Recall that if this hydrogen is coming here, it means here becomes CH2. Now, in this case, what do we have? This carbon is the one positive. Now, we can also have another situation where you have CH3. We have C. Here is what? CH3. And then this hydrogen attacks here, which is this hydrogen we are talking about. The hydrogen was the one that entered here to form CH2. It's now coming here. Then let's assume that the positive charge is on top of this one or here. Then we have CH3. Now, which of them do you think will form the major product and which do you think will form the minor product? Because naturally, when this attacks here, what do you say? It can attack the seat of this double bond, right? We say this bromine will come here. So this bromine is negatively charged and it's a nucleophile. The bromine can come and attack any of them here. So my question now is, which of them will form the major product? We know what a tertiary carbocation is at this point of our learning, right? We said a tertiary carbocation is a carbocation that have three different groups around it. For instance, if you look at this, this is a carbon center here. Then we have CH3. Then we have CH3. Then we have CH2 here. Now you see that in this group there are three different groups about the carbon carrying the positive charge. Are you getting it now? So this is a tertiary carbocation. Sorry, I've erased that. Here it's supposed to be CH3. Are you getting it? So here is a tertiary carbocation. Now how about this? Look at this one. How many groups are around it? You have this whole place considered as one group, and you have this one considered as another group. So here you have two different groups about it, and you call this a secondary carbocation. So which of them do you think will form the major product? Is it the first one or the second one? We say the major product is formed by the more stable carbocation. So the major product will be formed by the one with the third degree or the tertiary carbocation. So the major product will be formed in such a way that this Br will attack this positive charge here to form Br. Also, this one will attack here to form Br. And this is the product of this reaction. Okay? That's the product of that reaction. Now, the stability of the carbocation. We've talked about that, right? That tertiary carbocation are more stable than secondary, which are more stable than primary, which are more stable than methyl carbocation. Okay? Now, tertiary carbocation is one like this. or let me use a chi group to represent it. Okay, a tertiary carbocation is one like this, the one that you have C, arrow, 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 positive. This is more stable than arrow, C, arrow, H, positive. More stable than arrow, C, H, H, positive. More stable than C, H. You see that as we progress, you discover that the hydrogen increases and the methyl does what? Decreases, positive. So all these are these 3 degree, 2 degree, 1 degree, and what? 0 degree. Okay, so this how stable this carbocation is. You can decide to rule in line here, increasing or decreasing order of stability. Decreasing order of stability. Okay, so that is the product, or that is for the stability of the carbocations. Okay, so that is where we are going to end this lecture for today. Thank you for your time.